Sara Ferrón is our next speaker. She's an assistant researcher with the Department of Oceanography. She has a PhD in marine science from the University of Cadiz, Spain. I got all excited when Benedetto came from Naples and founded in 1224, so I looked it up for the University of Cadiz, 1979. She first came to UH as a postdoc in 2009, and her research interests focus on understanding the temporal and spatial variability in ocean productivity and the oceanic metabolic balance. Her talk is about measurements of gross primary productivity.
Hi, everyone. Thanks so much for staying this late. Thanks, Doug, for the invitation to talk today. So after we've heard Angel, Benedetto, and Seth telling us that we really should be moving towards autonomous platforms, I'm going to be giving a pitch to do some bottle measurements here. But I would argue that we have to keep any method that we have to measure primary production, because as Angel says, it's really very difficult to measure productivity in the ocean. And it's kind of hard to validate any single method. So I don't think by now I have to convince anyone that here in the audience that ocean primary productivity is important both in shaping the ecology but also the biochemistry of the ocean and really of Earth. So phytoplankton photosynthesis accounts for about half of the primary production of the biosphere, and that's despite the fact that phytoplankton accounts for less than 1% of the photosynthetic biomass, so that's pretty remarkable. And it, of course, as we've heard, affects the RC fluxes of CO2 and also oxygen, so in turn it affects climate. Again, it has a key role in many biochemical cycles, in particular in the carbon cycle, and it's actually the main source of both energy and carbon into the marine ecosystem. So it really provides the carbon growth and metabolic demands of really any other organisms in the ocean. So I was going to start by just giving you some terminology, and that's because different methods for measuring productivity really measure different terms, so it starts getting a bit complicated when you are trying to compare methods. Also, some methods give measurements in different units. So just to be clear, when we talk about gross primary production, we generally refer as that is the total CO2 that get reduced by the phytoplankton into organic matter. So you can think of this term as either the total energy flow into the marine system or the total carbon flow. But of course, a fraction of this organic carbon is going to get mineralized back into CO2, so with the remaining being the primary production. So you can think of this term more as the amount of carbon that is left in the ecosystem for the rest of the heterotrophic community. And of course, another fraction of this carbon is going to remineralize back into CO2 by the heterotrophic community, with the remaining being net community production. So really, net community production is the balance between gross primary production and the community respiration, with the community respiration being the respiration of both the autotrophs and the heterotrophs. And this is kind of as Seth was saying, one of the most important terms when you think about the carbon cycle, because it really gives you an upper bound of the capacity of the ocean to sequester CO2 from the atmosphere over a long time scale. So it influenced that. And again, I'm going to focus here on bottle incubations or incubation-based methods. And of course, there are other ways of measuring primary production, some of which I also use. I'm also interested in looking at dial cycles, but here I'm focusing on bottle measurements, which means that you collect a water sample, you incubate it over some time, you might manipulate it, and you measure a final product. And I guess one of the older methods is the light-dark oxygen method, in which you would measure the evolution of oxygen in dark and clear bottles during a period of 24 hours, and then from the net oxygen change in the dark bottle, you would estimate respiration, and from the net oxygen change in the clear bottle, you would estimate net community production. And you don't really measure gross primary production, but if you can assume that the respiration in the dark is the same as the respiration in the light, then you can add both terms and get gross primary production. When this method was developed, though, in the late 20s, the resolution wasn't good enough to measure productivity in low productivity environments. It wasn't until the development of the Winkler method and that was late in the 60s, that you could start using this method in a kind of lower productivity areas. But by then, another method had taken over, and that's the carbon-14 assimilation method. As Angel was telling us before, this is really the gold standard in oceanography for measuring primary production. And really what it does is that you add labeled bicarbonate and you measure how much of that labeled carbon has been assimilated into the organic matter. The problem with this method is that it's hard to interpret the results. It's hard to know really what you're measuring, and it depends on the length of the incubation. It is thought that over relatively long incubations of 12 to 24 hours, really what it gives you is an approximation of net primary production, but really somewhere in between net primary production and gross primary production. And that's because a large fraction of the assimilated carbon is going to be recycled back into CO2. The other problem also is that a fraction of this carbon is going to get partitioned into the dissolved organic carbon pool, and typically does not measure. So the way we terminate some of these incubations is just by filtering to a filter. So you are just really measuring the assimilation into the particulate organic carbon. But again, despite all these problems, this has been really by far the most utilized method to measure primary production in the ocean, and it's the method that is used really to calibrate satellite algorithms and other models. Another more direct method, but that has been less utilized, is the in vitro oxygenating method, and this really consists on adding oxygenating labeled water and then measuring the isotopic enrichment in the dissolved oxygen pool. And this is as a result of the splitting of water through photosynthesis. So it's giving you a measurement of gross primary production, or really gross oxygen production, as there are some, includes some oxygen production pathways that are not directly linked with carbon assimilation, but still, it's a measure that really you know what you're measuring, as opposed to the carbon-14 measurements, and also that is not affected by respiratory processes, and that's because the pool of oxygen is very large compared to respiration rates. And all of your label oxygenating is going into a very well-defined pool. But again, it hasn't been utilized very much, and that's because it requires an isotope ratio mass spectrometer that very few groups in the world have access to. So in the words of Falkowski and Robin, in their very famous book, Aquatic Photosynthesis, this is the 2007 version, when they describe this technique, what they say is that this technique allows a relative precise measurement of gross photosynthesis. However, the method is tedious, requires a bulky and expensive mass spectrometer, and hence has not been widely used in studies of aquatic photosynthesis in nature. Well, I'm here to tell you that we actually can measure gross primary production using the in vitro oxygenating method by using membrane inlet mass spectrometry. And what this means is that you no longer need a very bulky and expensive mass spectrometer. What you need is just quadruple mass spectrometer. These are way cheaper, so hopefully more accessible to more groups. And also they are very portable, so for the first time we can make these measurements at sea. And this is great because now we can have near real-time measurements, so this could potentially help with sampling strategy. You can feasibly collect more samples, and you really decrease the amount of time that the samples are stored, so it's great. But also, it's really technically easier. The sampling of the samples is much simpler. I'm not sure if you ever saw somebody sampling for oxygen isotopes, but it's really complicated. And sampling for membrane inlet mass spectrometry is really like sampling for a Winkler, and then it doesn't have any gas extraction step. So I'm not going to get into the nitty-gritty of the method, but I'm happy to talk about it if you're interested. And another very cool thing about this is that now you can get both GPP but also respiration even from the same bottle. So what we can do is that if we add oxygenating in a bottle, you can measure GPP, as we said, from the enrichment, the isotopic enrichment of the oxygen, but then we can also measure the net oxygen change during the incubation. So the net change and we do this by looking at the net change in the oxygen to argon ratios, which means that the difference between those terms will give you an estimate of respiration. And if this incubation, say you have an incubation that you go from sunrise to sunset, then what you would get actually is an estimate of respiration in the light. And this is very different from most estimates of respiration, because most estimates of respiration are in the dark. So you normally get a bottle in the dark, and you incubate it over time, as the net oxygen change will give you the estimate of respiration. So you could potentially have parallel samples and then see if really the respiration in the light is the same as in the dark, or whether nighttime respiration is the same as daytime respiration, which is a basic assumption in a lot of these methods, not only the in vitro method, but some of the dial methods that Angel was talking about. And just very briefly, I wanted to show you an example of a study where we've used this method, but of course, since 2016, I've been using this method a lot in a bunch of other studies. But just to give you a hint, this was a study that we conducted off the Big Island. It was a huge collaboration funded by NSF and the Simons Foundation, so a lot of, through the program of SCOPE, so a lot of SCOPE investigators. And this was during the 2008 Kilauea eruption, which you will remember. So during this eruption, there was a large amount of lava that started, so there was an extensive flow of lava that started entering the ocean. And soon after it started entering the ocean, what you could see from the satellite images of chlorophyll is that this was 3 days after the lava started entering the oceans. You see this plume of chlorophyll. And about 2 weeks later, this is how it looked. So there was this very large high chlorophyll plume that had extended up to 150 kilometers off the coast. And then it kept moving around, and eventually in August, when the lava stopped coming into the ocean, the plume quickly dissipated. So during the peak of this eruption, we managed to have a short expedition, a 3-day expedition. This was in July 13 to 17, and we went there and measured a bunch of different stuff. I'm not going to get into it because I don't think I have time. But part of the things that we measured were metabolic rates. And here I'm showing one of these satellite images, the one right before our expedition, with some of the stations that we sampled for metabolic rates. And we were also sampling a bunch of underway measurements. But you can think of Station 1 as a coastal station that wasn't really affected by the lava. And I forgot to say, but so it would be kind of a station of this blue side of the water, rather than this more like brownish lava impacted water. And then Station, oops, I'm getting ahead of myself. I know. Okay. Station 2 would be, Station 2 to 4 would be lava impacted waters, and Stations 5 and 6 were more oligotrophic. And that's based not only in chlorophyll concentration measurements, but also because we were measuring a bunch of trace metal and rare elements that we know that these were lava impacted. Well, we see that in addition to high chlorophyll and high biomass, we observe very high rates of primary production, both measured as the 14C assimilation method, but also measured as the oxygen 18 GPP method. These are 6 times higher than just the background oligotrophic waters. And also we were measuring respiration, as I just explained, both in the light and in the dark. And both estimates were relatively similar, but we did see an increase in respiration in the station that was closest to the entry of the lava, which I'm not too sure what was causing it, but maybe it was an external input of organic matter driven by the lava, or even a changing in the lability of the organic matter due to the high temperatures, not clear. But then one of our speculations was that the addition of iron and phosphorus from the lava, but the lack of fixed nitrogen species in the lava was going to enhance nitrogen fixation. But instead we saw that actually the nitrate concentrations were pretty high in the lava impacted water, and the nitrogen fixation rates were low. And long story short, because I think I'm running out of time, it turned out that the reason why there was a phytoplankton bloom was because of this lava-induced upwelling of nitrate-rich waters. I'm going to leave you with this page of my summary because I don't want to run out of time, but if there's any time, I'll take questions. Thank you.